And let me go over this second problem. The other ones I feel better about in terms of your understanding. This one has several components, and I want to make sure that you feel good about all of them. So let me quickly read us our equation. Use the table of atomic masses below, right? So this table over here, as well as the equation E equals mc squared to calculate the energy in kg m squared over s squared released based on the difference of mass. I'm highlighting a couple key words here. Difference of mass, calculate the energy, right? And these are going to be our units. This is how we're going to check if we did everything okay. And we're going to use the atomic masses below. So three key things, right? There's going to be a difference of mass. We're going to calculate an energy, and we're going to use these numbers below. Now, this might feel really dense. You might see the different pictures of the chemical equation, all of this table of numbers with really absurd numbers and then energy and this weird unit. Let's stick to these three things that we were asked, right? Ultimately, and I put it in bold for a reason, we're looking to calculate the energy, right? We're given our units. We can worry about that when we get there. We have to just calculate the energy. And it tells us that it's released based on the difference of mass. This is where our conceptual understanding of fusion comes into play, right? We know that in fusion, there's a ton of energy created. There's a lot of energy created, and this comes as a result of a loss of mass, right? If we're losing a mass, right? If we're losing heat, if we're losing money, we go on a quick trip, right? And we end up losing money along the day with our friends, right? Hanging out, and we're a couple dollars short. That means we started with a little bit more than where we ended, right? There was a bit more mass than there was at the end, right? We started with more, we ended with less. So the difference is going to be this minus this, right? Or actually the other way around. This subtracted from this, right? Subtracted, or this minus this second number. So we have to find the original mass first, the end mass then, and then subtract them, right? The end from the start, or the start minus the end, whichever one is hopefully best to appreciate. Same thing here, right? This and this, and then the energy is what we're looking for, and we're going to find it from that difference of mass. So this is where we need to be really clear about what mass corresponds to what. Let's put in blue what we start off with, right? Don't even focus on the name. It's a fancy name for your reference, but the important thing is that this is a 2H, right? As opposed to, for example, a 3H over here, right? Two different particles. They look differently, and they also have different masses. We look at our table down here, we notice that the 3H is about 5 times 10 to the negative 27, and then we have our 2 10 to the negative 3 times 10 to the negative 27. Sorry about that. Our last masses, what we end up with, right, correspond to helium, a much heavier particle. You can notice that it has like 2 protons and 2 neutrons, and I know that just because of the legend. We don't have it right here, but hopefully after some time you were able to notice that the gray is the neutrons in these examples, the red are the protons, and that matches up with this last one. So on one hand, we're going to be calculating our blue quantity with our other blue quantity, and we're going to subtract that from our orange quantity and our red quantity. Okay, so now it's a matter of literally plugging those numbers in, right? Adding all of those numbers together so that we can get some type of math. So let me just put that over there. I'm going to skip into when I actually add them and are subtracting them. I'm going to tell you how many times I tried doing this, because I ended up getting to the last step and finding some mistake in literally this step. So hopefully you're able to plug this into the calculator, get it to work, right? Just a reminder that these are all times 10 to the negative 27, right? And we can only do this because they not only have the same base, but also the same exponent. You can imagine all of these numbers being as ridiculously small as they are along the same decimal points, right? And it's 6 and 1, 3 and 5. It should be about 8 and 8 on the other hand. Now, this is where we can subtract one from the other. We notice that it's ever so small, but it's still true that the original mass, what we start off with, the reactant mass, is bigger than what we end with. And this is where we can finally plug that in, right? So that would be 8.3606 minus 8.32, and that's an 8 and a 4. We subtract this from the other, all times 10 to the negative 27. I'm going to plug that into my calculator. So that's 3284, and that's 8.3606, and we should get an end mass of 0.0322 times 10 to the negative 27, right? And a reminder that this is all in kg. We kept that constant, so we can just plug that back in there. And this is our different mass. It's super small, right? And technically the correct way to also write this is to move that decimal and have that be 3.22 times 10 to the negative 29 kilograms. So it's a super small number, but again, the important thing is it's not zero. When we plug this finally back into our E equals mc squared equation, we'll see that it's still a small amount of quantity, but this is one reaction. If you can imagine just a handful, even a dozen, right? Let alone a mole, right? This number is going to be massive once it happens often enough, right? These are atomic level interactions that are producing this amount of energy. So let's cut the talk and let's actually just plug this all in. This should be, we now have our mass. Once again, this equation is telling us how to use the difference of mass, which we found, into the equation E equals mc squared, where the speed of light is 2.998. So we have as our mass 3.22 times 10 to the 29 kg. Again, using 0.322 times 10 to the 27 also works. 2.998 times 10 to the 8 meters per second. All of that squared should give us, we plug this into our calculator, right? So let's really quickly do that. We got on one hand, let me do the speed of light first. 998 times 10 to the 8. All of that squared times 3.22 times 10 to the negative 29. And we should get, finally, so glad, this time I was actually right, 2 on my calculator, .989, my bad, times 10 to the negative 12. Once again, kg, the m squared, because that square applies to everything, over the s squared. We have our units that we want, connecting over here. This is our final energy. We'll get more into what this means, right, at a later point. That should be your ballpark area. If you got that a couple of decimals off, right, maybe like negative 14 or so, that's totally okay, right? It's complicated, and like I said, this took me, I'm not gonna say how many times, but a couple of times to get right. I kept getting a different number than what you all got. So that was actually how I was able to make sure I got the correct number. This is the ballpark, right? And if you can at the very least understand once again that we end with a different quantity than what we start with, and that you can plug in those numbers to figure that out, then you should be in good hands. I hope this was helpful, and let me know if you have any other questions.